Right, well, as people are taking their seats, thank you all for coming on our last Thursday seminar of term. It's a great pleasure to welcome Richard Healey back to Oxford. It's been a long time, actually, since he spoke at one of our Thursday seminars. We think it's 12 years since he last spoke here, so that's rather remiss of us, I'm sorry, not to have had you back sooner than that. But it's very exciting to have you here. So Richard, I'm sure, is a name that everyone will have seen on their reading lists and heard in discussions, since the name features on our reading lists and in our discussions so frequently in a wide range of areas. Richard's worked on a broad range of things within philosophy of physics. He started on his physics and philosophy journey here in Oxford back in the early days of the physics and philosophy degree, when it was just brand spanking new. As one of the first cohorts of students on that degree, on that degree course. But at the time, once he got to the end of it, there wasn't that much philosophy of physics else to do in Oxford by the time you got to the end of the undergraduate degree course, so he had to go somewhere else. And he ended up on exotic travels to Harvard to work on philosophy of physics there. And then still more exotic, some other Cambridge, I believe it's in the UK, where he was a JRF. Fell on his feet. Hume Miller was on a leave Hume leave, and so had some new unknown graduate students who needed supervising, and Richard very kindly agreed to take them on. These two young unknowns were Hugh Price and Jeremy Butterfield, who of course have grown into titans of the field. So Richard started out with an extremely strong track record in graduate supervision. Various positions in the States, and landed up at the University of Arizona, where he was for 30 or so years until recently becoming emeritus, now based in Spain. Over the last 15 years, I suppose it is now, Richard has been developing a novel kind of neo-pragmatist philosophy of science in general, with important lessons, he thinks, for how we should understand quantum theory in particular. And so this talk is part of that project of a revised way, a neo-pragmatist way of thinking about quantum mechanics. So thank you so much for coming, Richard. Lovely to have you, and over to you.
Thank you for that nice introduction, and thank you very much for inviting me back. Utopia. I'm glad to be here. I've been in Oxford a large number of times, very briefly, over a long period. I started out when I was 6 years old, and I came to visit my father, who just accepted a position in the university as a student. Anyway, I won't go into that because I've got a lot to get through today. So the title is How to be a Single World Quantum Relativist. There's a lot of this going around these days. A lot of it has been motivated by reflections on so-called extended Vignus-Franz scenarios. But there's more to it than that. This is not why I came to be a quantum relativist, although I'm happy to see reinforcements coming in for independent reasons at this point. I will briefly along the way mention a couple of other ways of being a quantum relativist to try to persuade you they're the wrong way to do it. But I'm not going to spend too much time on that. I have two agendas, really. The first one is to introduce you to this way of thinking about quantum theory. It's still not as popular as I think it should be. If you want more information on this, wait a while, because Oxford University Press is going to publish a book of my papers on this, I hope next year, but it's going to take a lot of work before they actually get it out, so I can't promise anything. The second reason is I'm going to try something new today as well. I'm going to raise objections against an argument, which is that if you're going to be a single world quantum relativist, you've got to go whole hog. You've got to go crazy. You have to be a relativist of finitely many iterative levels. And also you have to give up on what seems a very natural thing for a relativist not to give up on, namely that there's a possibility of some kind of communication between you and other relativists out there, as it were. So that is the new stuff, and I'm particularly anxious to get reactions to that. And I see that the main target of that is actually listening in on this, so he can see where I go wrong in my criticisms of an argument that came out recently, and Timotheus's Riedl's ownership. So let's get started then. And this is what you should be thinking about from the word go if you want to be a single world quantum relativist. What are you claiming to be relative? And what you claim is relative to? Is anything absolute? And is such relativism internally consistent? Does it all hang together? Or can you actually derive some kind of contradiction within? Does it help us to understand quantum theory? Or is it all just a sort of irrelevancy? Philosophical interest, but not interest in philosophers of physics. Finally, do we have objective evidence for quantum theory in this view? So those are questions any single-world quantum relativist should be asking themselves. Here are some references. These are the philosophical references that I want to give you. Some recent papers, a couple by me and then a paper by Timotheus Riedel. I hope I'm pronouncing his name correctly. I do my best. Okay, and that's what I'm going to be responding to towards the end of my talk today. I'm also relying on a bunch of physics papers, and I'll give you the references to them at the end. And when the reference sort of comes up, you will see it as I give the talk. So here's the plan then. I'm going to start off by motivating the talk. I'm going to talk about two kinds of relativity, I think, separated and discussed. First independently and then together, quantum state relativity and measurement outcome relativity. I'll briefly go through the scenario of Wigner's friend as an introduction to the current work, which we got from a lot of authors recently, extending the Wigner's friend scenario to many friends and many Wigners, just to make life more complicated, but allegedly to prove really interesting things that could not be proven within the original Wigner's friend scenario. Now, since my view relies on a notion of relative truth, the philosophers among you, well, probably all of you, I don't know, will get upset. What on earth is relative truth? I mean, it's hard enough making sense of truth. What's relative truth? I'll try and tell you. Then I get to my response to Riedel's recent paper. And at the end, if we get time to do this, I'll talk about answering my last question list I gave you. Why believe quantum theory in the first place if we don't have objective measurement outcomes to rely on as the evidence for this theory? Okay, so motivation. My motivation overall is to achieve a better understanding of quantum theory from as Chris nicely put it, a neo-pragmatist viewpoint. And what's this supposed to have as its payoff? Well, it's supposed to resolve the quantum measurement problem insofar as there is such a problem. It's supposed to show why there is no non-local action or influence. It's supposed to explain how measurement statistics support acceptance of quantum theory, which is something that everybody should be worried about. And finally, it's to evade alleged paradoxes extending that of Wigner's friend. But that is sort of not the main point of the program, as it were. But I only started thinking about this relatively recently, prompted by extensive interaction with Czeslaw Bruckner at Akoki in Vienna. Okay, so here's the part of more of the motivation. What is the role of a quantum state anyway? Well, in my pragmatist view, the primary use of a quantum state is to yield objective probabilities through an application of the Born rule. It's not to describe the world. It's not in particular to describe the multiverse or anything like that. Quantum theory's uses are not primarily descriptive. They're, as it were, prescriptive or advisory. So in this view of a quantum state, a system is not in a quantum state. You shouldn't use that language because it doesn't represent any of its intrinsic physical properties. On the other hand, a quantum state is assigned, but when it is assigned, it's assigned relative to a physical situation. And when that happens, the quantum state plays a different role. The main function, and this is not so surprising, is to yield objective probabilities by the Born rule. Although that they are objective is already controversial. And what is their function? Those probabilities. They're there. Their function within the theory and its applications is to offer advice on what might reasonably expected to happen in a context in which a system encounters certain physical circumstances. So they're not there giving you probabilities of what is the case. They're saying, this is the probability that such and such will happen in such and such circumstances if a system meets such circumstances. But there's a second function that, in my view, is important, and that's to offer advice on when and to what the Born rule may be legitimately applied. I mean, I think it's pretty well known that you can't go around randomly applying the Born rule to absolutely everything, assuming that what it's being applied to is a description of some state of affairs, because that will lead you into Cauchy and Specker type inconsistencies. Okay, so we need a rule for saying when can you legitimately apply the Born rule and when can't you? So from my perspective, the best way of thinking of quantum theory itself, actually there are many quantum theories, and David Wallace is exactly right to think of quantum theory as a framework theory, with many specific quantum theories within that framework. So each specific theory comes along with, or is associated with, a set of models. And what is a model like? Well, a quantum model always talks about some quantum system or systems, and it involves quantum states, or at least one. It involves time or space-time parameters. So if you're talking about unitary evolution, well, with respect to what? A time parameter. And it involves linear operators of one kind or another. And notice that all of these, except the systems, are mathematical objects. When I put up this slide in Vienna, and Seiliger said, what about quantum systems? They're mathematical objects too. In a sense, he's right. When you're working theoretically, you talk about a quantum system of a certain kind. You don't care whether the kind is physically realized this way or that way. It doesn't matter. A two-state system, what is that? Okay. But at the end of the day, if all you did was apply quantum theory to two-state systems, and you never actually got your hands dirty and said what a two-state system might be in the lab, that wouldn't be much good. Okay. So in an application of a quantum model, you apply the Born rule, and it takes different forms in different forms of quantum theory. But why doesn't it move on? I gave up the ghost. Well, too far now. Yeah, one thing I want to notice here, in this specific application of a quantum model, and throughout, I'm going to be talking about these things called magnitude statements. And a magnitude statement locates the value of a physical magnitude. Typically, physicists call these things observables, in a certain range. And that might be a unit set in particular cases, if we're talking about the value of that magnitude. Okay, so in my pragmatist view, a system's quantum state is relative to what I call a physical agent situation. And therefore, so are the resulting Born probabilities of these things I'm calling magnitude statements. What about magnitude? Well, a magnitude statement does not state the outcome of a measurement. It just states the value of a magnitude, or locates it within a certain range of values. That statement is made relative to what I call a physical decoherence environment. And that is modeled by a quantum state decoherence. But it's modeled by it, not by representing it. It's modeled by quantum state decoherence in the way application of a quantum model models anything, not by representing it, but by giving you advice about it. But notice here that a magnitude statement, although it is made relative to the physical decoherence environment in this view, is not made relative to an agent situation, or more precisely, it's not simply to an agent situation. The primary relatum is something different from the primary relatum of a quantum state on this view. But there's a rather intimate relation between the two relata. Importantly, the statement is accessible as true or as false only relative to a suitable decoherence environment. That's where a bit of relativity is coming in that's going to be important later. And so too is a claim about the outcome of a quantum measurement. So finally, I'm talking about quantum measurements and their outcomes because a measurement involves just such a decoherence environment. So in this view, there are magnitude statements which may be assessed as true or as false in universes with no observers making measurements. But it's not a coincidence that there are observers making measurements, and they make use of by producing just such decoherence environments in our world. Okay. So, relativity of quantum states. That's going to be the next bit. By the way, I'm going fairly fast over this stuff. You can read it in other of my papers or other people's papers because I want to get to the end of this talk. Okay. The quantum state is relative to a physical situation, which I call an agent situation. Here's an example. Suppose we're doing a familiar type of producing a familiar type of scenario involving entangled photons on which somebody is Alice and Bob are, and they're performing space-like separated projective measurements of polarization on each twin in an entangled pair in a particular Bell state. And we think of them machinations occurring within these space-time regions A and B. Okay, I didn't say performing their measurements in those regions. As we'll see later on, that wouldn't be quite the right thing to say here. But they're doing something. And this is what is the assignment of quantum states to Alice's photon relative to agent situations located in the relevant space-time regions. So to start off with, before anything has happened, as everybody agrees, Alice's photon is in a completely mixed state, and Alice thinks so too. And any guy out here, the space-light separated from both of those, thinks the same. But after Bob has performed his measurement, the state now assigned to Alice's photon, that's what the L is doing in here, is going to be an eigenstate of polarization, which is vertical with respect to Alice's axis. Okay. If you're worried about the asymmetry of this diagram, just interchange A and B and L and R, and it will be restored. Okay. It's asymmetric because we're focusing on Alice's photon state. Now, those are the state assignments relative to agent situation. I still haven't told you exactly what an agent situation is, but you're sort of getting the idea that an agent situation is associated with a space-time region, a compact space-time region. We look at the resulting relative Born probabilities. This is entitled The Chance That Alice Will Record Her Photon as being vertically polarized with respect to her little a axis, given that Bob has found his photon vertically polarized with respect to his polarization axis. This might, for those of you who recall what Bell says about this, realize that what Bell says about this is a bit confused, or at least confusing, because he talks about the chance. There is no the chance. There are all these different chances. And they're all objective probabilities, and they're all relative to different agent situations. Okay. And that's how the chances are. You could say that's how the chances change, but that would be a mistake, because the chances is specific to a region. Okay. So, what this means, more generally, is that quantum state and Born probability is relative to agent situation. Now, it's important to think a bit more carefully about what an agent situation is. First thing it is not is an agent. And it need not be occupied by any agent. Well, it might be, and it sometimes is. Agent situations are physical things. They might exist even if there were no agents. And as I already mentioned, an agent situation includes a compact space-time region capable of accommodating a spatio-temporally localized agent. But, and this is an important difference between agent situations and agents, a single persisting agent may occupy multiple agent situations, each at a different location in its world tube, as it life goes on if it's alive. But this is something that we'll soon come to see an example of. To play its role as a launch pad for assignment of objective probabilities in this view, an agent situated in an agent situation has access to information that may be limited by more than just its space-time location, as we'll see already in the scenario of Wigner's friend. It's not his space-time location that renders him cut off from any direct observational access to what's going on in his friend's laboratory. It's the physical isolation of his friend's laboratory. Okay, now this is stuff I've believed for a long time, although the notion of an agent situation gradually came into focus over the years. But then we get to something which is more radical, namely the relativity of measurement outcomes. And the claim here now is that a measurement has an outcome only relative to a decoherent environment. That's a summary of this entire short section, so let's go into the section. What's a quantum measurement anyway? Well, Wigner, in his famous paper, followed Dirac and von Neumann in taking a quantum measurement to involve a nonlinear physical process of state collapse, reduction of the wave packet or whatever. But there's an alternative view of what's going on here, according to which what's involved here is a discontinuous change of state on measurement, not as an indeterministic physical process, but as simply the bookkeeping exercise of updating information to reflect the outcome. Schrödinger talked about bookkeeping way back in 1935, and it seems like a good metaphor. But it raises an obvious question, right? Who keeps the books? Well, a standard answer, well, it's just the observer. What's that? An agent, such as a friend like people we're going to meet soon, Charlie, or a super observer like Alice exerting quantum control over Charlie. But quantum theory, in my view, is not a theory of agents. I've got the stress wrong. It's not a theory of agents. Although it was developed by agents, physicists, for agents, capable of successfully applying it. If you like quantum theory is not like democracy. Right? People say democracy is rule of the people, by the people, for the people. Right? Quantum theory is not like that. It's not of the agents, but it's by the agent and for the agents. Okay. On this view, quantum theory may be applied even to a possible world in which there are no agents. A system's quantum state is always relative to some agent situation. To update that state is just to switch one's attention to the state relative to one agent situation to the state relative to a different state agent situation. Typically, one from which additional information will be epistemically accessible, including in particular the outcome of a quantum measurement. So the agent applying a quantum model is the one who keeps the book, whether or not that agent appears in the scenario to which the model is applied. Okay, so that's all very nice, but what is this decoherence environment I keep talking about? Here's my attempt to tell you. An M decoherence environment I'll call E of a quantum event, E, little e, in which a magnitude on a system may be said to take on a value in the region of space-time, R of E, that includes the region where E occurs, together with physical processes in that region that can be modeled by decoherence of that system's states in a pointer basis associated with different values of M. Such decoherence is robust in the sense that once a process starts, the system's reduced state, when we trace out all the other stuff in the larger system of which the subsystem is a part, remains very nearly diagonal in the pointer basis throughout that space-time region. And M equals M says that event E occurs in region R sub E. Okay, but since a physical interaction in a quantum coherence involves unitary evolution, there's always going to be a formal extension of that model outside of that region, in which a second unitary reverses the evolution, thereby restoring the original coherence. And the event may not be said to occur relative to that extended region, which is not an element of an M decoherence environment of that event. The occurrence of an event is relative to the decoherence environment. Has it really happened? Well, relative to this decoherence environment, yes. Relative to this larger environments, we formally extended it so that there isn't any overall decoherence. Silly question. There's no decoherence environment with respect to which to ask that question now. Now, what about quantum measurements? They occur, on this view, in decoherence environments. A quantum measurement involves an interaction modeled by quantum decoherence in an appropriate decoherence environment. Again, modeled by, what does that mean? Described by, represented by? No, it doesn't mean that. It means you can apply the model in that situation. And when you do, the model tells you, advises you to believe that it's a decoherence environment. Now we get the way in which the Born rules application is licensed. The Born rule may be legitimately applied to events in an appropriate decoherence environment. It follows then that the Born rule may be legitimately applied to events with the possible outcomes of a quantum measurement. We've gotten back to talk about quantum measurement outcomes, not by starting out by stating the Born rule in terms of measurement outcomes at all, but making the link between decoherence and outcomes in the way I've indicated. Now, if you think back to what I said before, you'll see that, look, a decoherence environment, what is a decoherence environment, is going to be relative to the quantum state, which you're using to decide that it is a decoherence environment. So if the quantum state itself is relative to an agent situation, so also is a decoherence environment. It inherits the relativity of the model's quantum state. This is what I didn't understand adequately for a long time. And therefore follows that the occurrence of a quantum event, such as a measurement outcome, is relative to an agent situation. But a single decoherence environment may be related to more than one agent situation, and so remain fixed as those agent situations are varied. If you remember the picture I showed you before, those numbers for quantum state assignments and the consequent Born probabilities were rather randomly located within regions of space-time. You can shift things around within such a region. It doesn't change anything as far as the relevant decoherence environments are concerned. So there's some flexibility here. But a decoherence, I just said that, may be insensitive to the precise space-time location of an agent situation. On the other hand, the picture I showed you also indicated that the objective probabilities and the quantum state assignments did depend on agent situation somewhat, and therefore so would any associated decoherence context. So here's a question that we should all have an answer to. When is a quantum measurement? Okay, let's start off with something I'm going to take for granted, that information about an event E is epistemically accessible through observation, if you like, from an agent situation S only if E lies in or on the past light cone of S. So, in a pragmatist view, a quantum measurement may be said to have an outcome only relative to a suitable decoherence environment. Hence, the outcome is going to be observationally epistemically accessible from S only if the region of the decoherence environment lies in or on the past light cone of S. Going back to the point I made earlier, which we always have to bear in mind, especially in the context of extended Wigner's-Friend scenarios, if decoherence in E is subsequently undone by a reverse unitary in a region that extends the region of decoherence, that we're talking about, then no quantum measurement is said to have occurred relative to that extended region. It's like we've sort of undone the quantum measurement, but that wasn't quite a good way of putting the point. There no longer was a quantum measurement relative to the extended region. Okay, so now we're going to go into stuff about extended Vignes-Friend scenarios, and the first step there is to look at the original Vignes-Friend scenario. I have shamelessly stolen this lovely picture from Czeslaw Buchner. All credit to him. We haven't got the picture yet, sorry. Here it is. Exactly what the friend measured. Wigner himself didn't have a spin-half particle. He had something else. It was a superposed state that the friend was measuring inside her completely physically isolated laboratory. And what did the friend and Wigner disagree about, according to Wigner? Whether there's any outcome of the friend's measurement. What's the resulting quantum state of her laboratory and its contents? What's the probability that Wigner will observe a particular outcome when entering the lab? And, okay, I think we're doing all right still. Here's what Wigner originally said in 1961. He seems to have changed his mind subsequently, but I haven't followed the history in enough detail to say where and how. Okay. Now, this is what Wigner said. His friend's consciousness collapsed the lab's quantum state, leaving her particle in an eigenstate with the eigenvalue recording her outcome. And after the collapse, friend was right, and the Wigner outside her lab was wrong about 1 to 3 that I just went through here. Okay. So he took the friend's side, but his resolution attributes strange physical powers to something of which we still lack any scientific understanding or even any very clear concept, namely consciousness. Okay. So there seems to be an alternative resolution available. There is no collapse. Quantum state evolution is always unitary. But the eigenvalue-eigenstate link is false. The friend's measurement has an outcome that is recorded in her lab, which the Wigner comes to know only after entering her lab. But unitary reversal of the quantum state of the entire lab, absent Wigner's entering the lab, would erase all traces of this outcome. And this is the way I see arguments based on extensions of Wigner's original scenario. They've cast doubt on this alternative resolution, which I was quite tempted by for a while, by putting more pressure on the idea that the outcome of a quantum measurement is an absolute fact. So how do we extend Wigner's friend? We add more friends in isolated laboratories, each with its own external Wigner, which is usually called a super observer. Super because this thing can not just observe, it can manipulate in an exquisitely detailed way. It can exert any kind of quantum control of the contents of its observer's laboratory, including the observer itself. So here's a schematic account of one. Each friend is an agent confined to a different physically isolated laboratory, which they measure a magnitude on a quantum system and know the outcome. There are the super observers. These are also agents. They have exquisite quantum control of everything in their friend's entire laboratory. And then what does the super observer do? It has a choice, and that's going to be important. But one thing it can do is unitarily undo their friend's quantum measurement by manipulating the entire laboratory containing the friend, and then measure a different magnitude on the entire laboratory, including the friend. Alternatively, they can perform a very specific, precise measurement on their friend's entire lab without undoing the quantum measurement. That also, like the first one, erases all of the friend's records, memories of their own measurement outcome. I'm going to focus on the scenarios that take the first option today, to be a bit more specific. And they give rise to arguments started, as far as I know, with Czeslaw Buchner, but have proceeded through many iterations, getting better and better, against absolute facts. No-go proofs developed for an extended Wigner's friend scenario. There's a famous proof offered in a paper by Bong et al. I'll give you the reference at the end if you don't know it already. They derive probabilistic local friendliness inequalities, their name for absolute outcomes, in one EWFS in violation of quantum predictions. And Hadara and Cavalcanti followed up with a similar argument based on a Hardy state, which is possibilistic rather than probabilistic. It relies only on what is possible or what is impossible in the sense of probability greater than 0 and probability 0. There are a whole bunch of other papers by Cavalcanti, Howard Wiseman, and so on, that I don't want to get totally lost in the weeds here, although it's unfortunate to call these rather lovely papers weeds. Okay. So here's a principle they use in such arguments, or at least the more recent ones. A principle they call local agency. This is a kind of locality principle, but it's much weaker than Bell's locality or factorizability or something like that. A super observer's choice of measurement setting is uncorrelated with any observed event outside its future light cone that plays a role in the scenario. Now, these arguments don't go through if the outcome of a quantum measurement is not absolute but relative to the observer. But it's important to stress that there are other ways out, because there are other apparently very plausible assumptions that go in as assumptions of the no-go theorem. And you can always get out of the conclusion that outcomes are relative by dropping one of those assumptions. But then you have to face the consequences of giving up on something which you really don't want to give up on. Okay. But then let's come back to the worry. The principle of local agency talks about observed events and super observers. What are those things? What is an observer, and when is an observation made? Here's a picture which this time I have modified from the Bon et al. Paper. The lovely picture on the right is from the paper. The words on the left are modified a little bit from the words they used to accompany this. Okay, I think you can read that for yourselves. There are various variables floating around here. X and Y represent possible choices either of Alice or of Bob. And A, B, C, and D represent the outcomes of what these guys have done given the choice that has been made. Okay. So here's the idea, if you're not familiar with this. If you are, then you don't need this slide. The problem is that the outcome frequencies, if one were to perform this Gedanken experiment, would not match their quantum probabilities. Specifically, if you assume, okay, I'm getting too much into the weeds. Basically, the probabilistic correlations between pairs of outcomes predicted by quantum theory are incompatible with the existence of a joint probability distribution for all of the outcomes at once. So if the quantum predictions are correct, then at least some of those measurement outcomes must be relative and not absolute, given the other plausible assumptions. So this is a rather lovely argument. The specific sort of proof of principle experiment that they went on to do, I don't think has very much weight. It was too far distant from an actual observer, actually observing anything, to show that this has been proven experimentally. Okay, so what happens if you deny absolute measurement outcomes? Well, I've already given you independent reasons for doing that follow from my neo-pragmatist take on quantum theory. But I won't go through that again. Let's just assume that there is no joint probability distribution for all these outcomes at once. Okay, so all of those outcomes are just relative. What's that? What is a relative fact? If you're a philosopher, you should be getting very upset at this point, I think. Is there an absolute fact about Alice's or Bob's measurement outcome when this thing is all over? They were the super observers. They're supposed to know everything that could be known from the outside, as it were. Is that an absolute fact? And this fact, this question is what I'm going to go into in more detail. Is there even an absolute fact about a relative measurement outcome, assuming that measurement outcomes are accepted as relative, are there absolute facts about them? And finally, I can see I'm not going to get to, if there are no absolute facts about quantum measurement outcomes, do the statistics of the outcomes of the quantum measurements we have performed give us any objective reason to accept quantum theory in the first place? I think they do, but it takes quite a bit of argument to show that, and hard thinking about what you're talking about when you use the word objective here. Okay. So, what's a relative fact? Here you go. A perspectival statement, I'll say more about that in a minute, may be accessible for truth or falsity only at an appropriate context. It's not a context at which a statement is made, it's a context at which a statement is assessed, if it can be assessed at that context. If it's assessed at true, it states a relative fact, a fact relative to the context. And the perspective of context is all of the things that are true relative to that context. Okay, that's a bunch of analytic shopping, if you like. What is a relative fact anyway? Okay, so if you're a pragmatist, you have views about truth and its relationship to facts. Analytic philosophers have beaten up on William James's view of truth, starting with Russell and Mill, who rather uncharitably read what William James wrote, but he should have written something clearer. There is no one pragmatist theory of truth. It's a big mistake to identify pragmatism with the pragmatist theory of truth and identify that with the sloppy things William James said about truth. There are alternative things, much more interesting things that pragmatists have said about truth. Charles Peirce said more interesting things. Frank Ramsey said much more interesting things. And the contemporary neo-pragmatists have developed views pretty similar to Ramsey's, although, again, different in details. The basic thing that all pragmatists do think about truth is that to say it's correspondence to reality is a waste of time. It's either vacuous or tempts you into unprofitable metaphysical speculations. That's not a good thing to think about truth. And I'm giving you a thing to say about truth in relationship to facts. Just to introduce the notion of a relative fact. And, you say, well, what do you mean to say that a statement is true? Well, a statement is true if it means true. That's it. Don't go off into correspondence theories, truth as warranted assertability or coherent, anything like that. Just keep it plain and short. What's a fact? Well, a statement states a fact if and only if it's true. That's it. Well, if we believe that about truth and facts, we can develop corresponding relative notions by these alternative principles. I've stated them here, so I won't read them out again. And again, a context is a context at which a statement is accessible, not a context in which it is made or used. So now we have a very wide-ranging take on what relative truth is. One philosopher who's done some very interesting work and applied the notion of relative truth to things that has nothing to do with quantum theory is John McFarlane in a book called Assessment Sensitivity. He and I, if we were together in the room, would disagree about a lot, but I think that he's come up with some very nice sort of formal constructions that I can apply for different purposes to quantum theory. Okay, notice then that when we find the application to quantum theory, we're going to be saying that there are certain contexts for which no simple notion of truth and fact is applicable. Don't ask whether it is the true outcome of this quantum measurement. It's a bad thing to ask about because the notion of truth is not going to be applicable in the first place, only relative truth. So let's plunge ahead. And we know all the pieces to do that. A magnitude statement is accessible for truth only at a context provided by an MD coherence environment of E of S, in which case it may be true relative to E or false relative to E. It can't be assessed at all outside of such a coherence context. That's the same thing applies for outcomes of quantum measurement. A statement of the outcome of a quantum measurement on a system is accessible for truth only at a context provided by an anti-coherence environment of a system indicating that outcome, in which case it may be true or it may be false relative to that context, or relative to that decoherence environment. That is the context. A statement about the outcome of a quantum measurement is never simply true or false. There is no absolute fact about the outcome of a quantum measurement. So this is all the sort of formal mechanisms for talking sensibly about relative truth and relative facts that's available to somebody who wants to talk that way. And it's a good thing it is available, because that's what I want to say about measurement outcomes in quantum theory. Okay, so what is it relative to? Remember the questions from the beginning? Outcomes are relative, but not to observers. An observer is not a conscious being. It's not just any physical system, as Carlo Rovelli says it is in relational quantum mechanics. It's not an agent able to use quantum theory, as cubists say it is. In my pragmatist view, a measurement outcome is not relative to any such observer. It's relative to a decoherence environment. That's what it's relative to. But in an extended Wigner friend scenario, each friend does open a primary decoherence environment that their super observer then modifies in various ways. So, more questions I raised. Is there an absolute fact as to Alice's or Bob's outcome, the super observer? Basically, no. They're just in the same situation as Charlie and the mere observers. But look at the decoherence environment of Alice and Bob after they've done their thing. Both of those decoherence environments can be extended into a suitable joint environment. Alice's and Bob's measurements will both have outcomes relative to their joint decoherence environment. So there's a kind of coming together here. Truth facts are still relative, but they're relative to something bigger that incorporates more actual agents in this context. Right, so what about relative outcomes? Here we get to Riedel's really nice paper. He's argued in a recent paper that's now available on the BJPS recently website, that quantum relativism is untamable. Nice word, right? A consistent quantum relativist, he thinks, who accepts the conclusion of an EWFS no-go argument must both give up on sort of communication between agents, cross-perspective communication, and accept that the relative measurement outcomes extends to higher order relativity. You're not just relative about the measurement of outcome, but you're relative about the relativity of the measurement outcome, and it goes all the way up, finitely at least. So here's what I want to say in response to that. A pragmatist insistence on relativization of outcomes to decoherence environments, not to observers or other quantum systems, is key to taming Riedel's, apologies, he's listening. Relativism. Okay. He gives us a revenge argument modeled on the no-go theorem, but starting off with the assumption that there are absolute relative facts, not just absolute facts. And he uses a relativized tracking condition, which is intended to secure cross-perspective communication in the argument. The word tracking originates in a paper I'll give you the reference to at the end, a survey of all kinds of EWFS scenarios and arguments, which is rather lovely and very necessary if you want to get into this business. Okay. The word cross-perspective dates from a revision, or I take it to be a revision, in relational quantum mechanics that appeared in a joint paper by Carlo Rovelli and Emily Adler a while back in Foundations of Physics. So here's the relativized tracking condition. O, observer, whatever that is, measures a suitable pointer variable of O star, another one of these things. The outcome of this measurement relative to O accurately reflects what the outcome of the corresponding previous measurement by O star at issue was, relative to O star. So we get relativity of this outcome to one observer, but it's the same outcome relative to this other observer. That's the idea. So we get some kind of possibility of communication between observers about relative outcome. That's the basis. Okay. Well, along with others, I take a no-go argument to show that measurement outcomes are relative in universe and not absolute. And the parallel no-go revenge argument tries to use the same strategy to show that relative measurement outcomes in that situation, in that scenario, are themselves relative, not absolute. So if this strategy works, it can be iterated to arbitrary finite orders of relativization of the original argument. All you have to do is at each order impose a sort of nth order tracking assumption. Okay, so here's a picture of the kind of scenario I'm going to be talking about now. This is from the Heller and Cavalcanti paper, and it gives you the space-time location of various things. C and D are when Charlie and Debbie are messing with the systems to which they have access. X and Y are the points at which Alice and Bob make a decision as to which of two actions to perform. A and B are regions at which Alice and Bob perform the actions they have earlier decided to perform. So what's going on here? Well, Charlie and Debbie, it's easy to say what they're doing. They're doing the same thing every time. They start off with this Hardy state, an entangled state between two qubits. At C, Charlie arranges his particle to interact with the system, which I called little c in a way modeled by the following unitary transformation. We're not collapsing things, right? We're unitarily evolving them. And Debbie arranges for her particle similarly to interact with the system little d in a way modeled by the similar unitary transformation. Now, I'm going to say neither of those interactions is a measurement. They've done something, but there is no measurement outcome yet. We don't have any decoherence environments around right now. C and D are not regions of decoherence environments. Some people, like Sir Reck, call them pre-measurements, since measurement further requires environmental decoherence of little c or little d. So we have to wait a while, as it were, in each case within the light cone after Charlie's interference and the light cone after Debbie's interference before we actually got a measurement outcome. What about Alice and Bob? Here it gets a bit more complicated. I hope that you follow this. I guess you have to read the original paper and then remember what I said about it, which is asking a lot, but that's what I'm asking you to do. All right. At X, Alice freely chooses between different actions to perform at A. Each model is a unitary transformation here. One thing she can do is pretty straightforward. Measure Charlie's pointer observable. What did you get? That's the sort of operationalizing of asking Charlie what he got. Option 2, close the primary decoherence environment of Charlie and of Debbie, thereby restoring, and Debbie. Alice can't do that. Okay, I didn't talk about what Bob is doing. It's Bob who can close Debbie's primary decoherence environment. This is not quite correct. Okay. Restoring the entangled Hardy state of the two particles, and then measure her own particle in an incompatible basis. Okay. Those are the options they have available to them. Charlie and Debbie always do the same thing. Okay, so we start off with 4 joint Born probabilities, each for the outcomes of a pair of measurements by Alice. And now the notation is going to get a bit upsetting. If we have a prime over something, it just means, we're only considering this as a relative outcome, not an absolute one. Okay? And a relative to the measuring observer. And the first of these things, an outcome that's going to feature in a joint probability, is the outcome of Alice's measurement, either on Charlie's pointer observable, if you chose option 1, namely to measure it, or on her own particle, if you choose option 2. The second thing we're going to look at in a joint probability has not just a prime, but an asterisk as well. What's that? Well, that's the outcome of Alice's measurement on Bob's pointer observable, whose value records the outcome of Bob's chosen measurement, either on Debbie's pointer observable, if Bob chose 1, or on Bobby's own particle, if he chose 2. And Riedel assumes the tracking condition for relative outcomes and the relativized form of the local agency, which is what went into the original no-go theorem. The choices of measurement settings made by Alice and Bob are uncorrelated with the outcomes of any measurements relative to the respective experimenters that are relevant for the scenario and occur outside the future light cones of those choices. So these light cones are going to be important. So let me flip back a bit so that you see where they are. This is where they are. No, what happened? Yeah, all right. So this is Charlie's machinations, Debbie's machinations, Alice's choice, Bob's choice, Alice's machinations, Bob's machinations. Okay. So see if you can sort of get those light codes internalized in your thought as I continue. Good luck. All right. Okay. So what are these joint probabilities if we actually evaluate them using the Born rule, which we're allowed to do because we're assuming the Born rule is right. Okay. This is what they are. The joint probability, given that Alice has made choice 1, that's measuring Charlie's pointer, that she will get 1 having measured his pointer, and that she will get 1 for her own measurement, okay, for her own outcome, measuring what she did, not measuring Bob's pointer, but measuring her system, okay, whatever it is. Similarly here, but this time we've taken the case. This is the case where Bob chose to measure Debbie's pointer, and this is when Bob chose to measure his own particle. Alice didn't, because we still got 1 there. Okay. And this is a similar thing. All these probabilities are 0. That's what's so cool about the Hardy state. But this one isn't. Okay. And all right. We haven't got where we're going yet. We haven't got a contradiction yet. So far, so good. But here's the contradiction coming, right? If we apply the tracking assumption, the relativized tracking assumption, we're supposed to be able to get from those probabilities with A's in them to probabilities with B's and C's and D's. Okay. And then if we apply local agency, we can go further and we can say, look, all of the 1s in here could equally well be replaced by 2. What would it matter? Because local agency says it's only what happens in the past light cone that counts. What happens in the future light cone doesn't matter. So we can switch 1s and 2s around, and we get the same stuff on the left, but different stuff on the right. And those 4 are inconsistent. So not even relative outcomes are absolute if we assume the tracking condition, the relativized tracking condition, and the relativized local agency condition. It's a cute argument. I don't think it works. What Alice measures depends on her choice between 1 or 2. And the tracking assumption is applicable. So A prime equals C prime. We got rid of the A prime and replaced it by a C prime. Only if you choose as 1. And the same thing applies to Bob. Those restrictions block the subsequent application of the relativized local agency condition because there's no reason why A prime equals C prime or B prime equals D prime for the respective choice 2. Okay. So here's what I'm saying. we can't replace A's by B's and C's and D's unless we're allowed to do so. And we're allowed to get that far, but then we can't apply local agency because the values are still okay. We can still replace A's by C's and D's and so on. But here we've replaced what the choices were, where the ones have been replaced by twos. And when we've done that, we've done something illegitimate. Because now we're actually making an assumption about a local agency, which is applying it, as it were, indirectly to the A's and B's that we got rid of. And they lay in the future icon, not in the past icon. I hope that kind of gives you the idea of what goes wrong. I don't expect anybody to believe me because I haven't had time to be more patient in presenting the idea. So go to it and see if you can retain enough traces of what I've said here to reconstruct my objection. Okay. More concretely, if anybody wants a copy of these slides, I will send them to you. But the slides have a bunch of formalism, but not enough words to talk you through it in the way I've tried to do. Too quickly here, and already I just finished.
Yeah.
Okay, so I'll just cut all of this stuff from here on in. I first of all propose the ways of modifying what Riedel is doing within my framework, showing that there's no contradiction, but making a little more progress by replacing all talk about relative to observers by relative to what it should be relative to, namely the coherence contexts. And then the last section is just dropped, probably, fortunately, because I'm not sure I even believe it. Thank you.
Thanks, Richard.